Guess we better get started. Exam 2 will be in Brightspace, the same way as before, which reminded me that one thing I didn't hand out was the sample exam for Exam 3. So I checked, and it's right here in Brightspace. Scroll down, there it is right there. Okay, so there's your sample exam right there. If you want some practice. All right, stop that share. And we're going to kick off with Chapter 6. I'm starting to get into actual reactions now. Jump to a slideshow. You'll notice in the schedule that I've got arrow pushing videos. There are 2 of them, and the links are in Brightspace. They're excellent videos. They will explain arrow pushing to the nth degree, which is probably more information than you need. But we're going to look at a little bit of arrow pushing in this chapter. So it'll give you an orientation as to why arrow pushing is used and the advantages of using it. So, chapter 6, Dr. Carty is going to use proton transfer reactions to introduce concepts of mechanisms. And that's where arrow pushing comes in. When you go, remember from general chemistry, when we talked about chemical kinetics, or when you took it someplace else. I hope that the concept of mechanisms was introduced, elementary steps. So when you're looking at a reaction like this, actually it'll have coefficients too. This is an overall reaction, and there could be 1, 2, 3, or a dozen different steps that happen right in here. You go from here to there eventually, but you have to go through these steps. And there are very few reactions that occur in only one step. Most of them are at least 2. So that's the idea that we're carrying over into organic mechanisms. Okay, so I've already mentioned this part of how the reactions take place in steps. These are elementary steps. And sometimes they can explain why the reaction occurs. And that's particularly true for organic reactions, because we want to be able to predict the outcome, if at all possible. As most organic chemists, when they actually get a job, their job is to make stuff. Sometimes they make new stuff, sometimes they make old stuff, and if you know how the reaction proceeds, then if there's a problem, it's easier to figure out where the problem is. So from now on, the textbook and what I'll try to present is reactions in terms of their mechanisms, because there are only a handful of mechanisms that will explain all of organic chemistry. And we pick and choose from those mechanisms depending on the circumstances. The reaction conditions dictate which mechanisms are most favorable. So actually, if you understand these principles, remember Bronsted and Lowry, acids and bases, right? Acids are proton donors, bases are proton acceptors. And we also get into Lewis. Let's see, let me be consistent here. Lewis acid, Lewis base. You don't have to have protons to have a Lewis acid or a base. If the acid is a proton donor, then the Lewis acid would be an electron pair acceptor. So a base would be an electron pair donor. Okay. And the other two concepts are, and we'll get these eventually, but I'm going to put them up here so that they all, you see them all together. Let's see. Let's put this one as 1, 2, 3 is nucleophiles. And the last one is electrophile. Okay. I'll just leave that for now, and we'll talk about those in detail later. Okay, so for a proton transfer reaction to occur, the one concept that I try to teach my general chemistry students in when we cover acids and bases is that protons never occur free floating in the solution. I mean, sometimes we write equations like that, but we have to understand that protons are always transferred from one place to another. They've got a home, they're going someplace else, they're going visiting, but they never occur by themselves. So if you see a proton in the mechanism, be suspicious. Okay. So in this case, we've got a simple proton transfer reaction in which a base, a hydroxyl, is accepting a proton from hydrochloric acid. So the proton goes to the hydroxide anion and makes water. And the proton is colored in blue so we can follow its progress. And then what's left behind is the conjugate base. So remember the acid base, when the acid undergoes a reaction, it produces a conjugate base, and the base produces a conjugate acid. And remember the relationship, if you have a strong acid, you have a very weak conjugate base. Or if you have a weak acid, you have a very strong conjugate base. That's one concept that we need to hold on to, because in some organic reactions, you need a very strong base. And this is one of the strongest. It may not be the strongest, but it is very strong. The hydroxyl anion. The reason it's very strong is because water is a very weak acid. Right? So that makes this the strong conjugate base. Right? Remember when water dissociates, and this is one of those cases where I'm going to break the rules. When water dissociates into that, now this is okay, right? But that's not what actually happens. But for calculation purposes, it works out just the same. And the dissociation constant for this, the ionization constant, is 1 times 10 to the minus 14, right? So that means that there's very little of this in solution. When this is produced, it wants a proton really bad, and it's going to take it from wherever it can get it. Okay, this just a refresher. So when we look at this proton reaction, this example of a proton transfer reaction, a bond has to be broken and a bond has to be formed. So the acid, remember, acids are, I think I'm safe to say this, acids are covalent compounds. Now the bond might be weak, especially for strong acids. The covalent bond with the proton is relatively weak. That's why it's released easily and produces strong acidic solutions like hydrogen chloride in aqueous solution will transfer that proton in a New York second. But that bond has to be broken. And once that bond is broken, it can form a bond with the hydroxyl and create water. This term that I bolded here, concerted, you know what concerted means? The bond breaking and the bond formation all happen exactly the same time. Now, we may represent them as individual steps, but this happens at exactly the same time. So what you would see is this hydrogen chloride and this hydroxyl. Let's see, let me put this out here. No, that's the way they do it. They put the hydrogen on this side. Okay, so as this bond breaks, and you would form an intermediate with a partially broken bond here and a partially created bond here. Okay, so these electrons are starting to go that way, and this electron pair is starting to go this way to form the new bond. Okay, that's what we mean by concerted. Happens at the same time. So now we get to the curved arrow notation. A curved arrow in organic chemistry always means the movement of electrons. So if we have a curved arrow like that with a double head, that's an electron pair movement. Okay, we will have examples in the future, not many, but a few. Okay, so far? Yeah. Really? Oh, let me see.
I think the one online getting previous.
Yeah.
Yeah, it is different. Uh-huh.
I mean, I don't know if it matters.
It should. It should matter. I mean, presentation might be different. Yeah, back up. Didn't say what edition. But it has different, just have a different appearance to that front page.
It doesn't have the second slide.
Yeah, it doesn't have the slide that I was looking for it.
Yeah, it's a different. See it's slightly similar, but it's a different. Yeah, this is the third edition. I must have left the first edition in Brightspace. Okay, I need to change those. All right, let me go back. You should be able to follow along though. And the hard copies are going to be third edition.
Yeah.
Okay, so the curved arrow means movement. If it's a double barbed or a double-headed arrow, that's a pair of electrons. If it's only a single barb, that's the movement of one electron. And usually when you see one of those, you'll see another one go in this direction for the other electron. So this typically occurs when a bond breaks. But most of the time, you'll see the double barbed arrow. One example where this occurs, because when that occurs, when you break a bond and you split the electrons that way, you usually end up with a free radical. And everybody used acne cream with benzoyl peroxide in it. Yeah, that's what benzoyl peroxide does. It has a very weak bond between the two the two groups. I can't think of the names right now. But the bond breaks and electrons go in two directions and produces a free radical. And free radicals are deadly to microorganisms, which is why it's good for skin infections. Okay. So the other thing that you'll consider with curved arrows is curved arrows always originate in one of two places, either from a bond, that is the tail starts at a bond, or starts at a lone pair. All right. So that first one, first step, the left-hand arrow starts at a lone pair, and its destination is the hydrogen because it's trying to form a bond. And when it does that, we can't form a bond with that hydrogen yet completely because it's already bonded, right? And hydrogen can only form a single bond. That's it. So we have to break the bond. So the bond electrons between the hydrogen and the chlorine have to be sent over to the chlorine to make a chloride ion. So this reaction requires two arrows. Okay, that's a good point. The number 4 there, I think number 4 on yours is that same thing. If a curved arrow points to another, to an atom, it represents the formation of a sigma bond if the electrons originated from another atom. Now, sometimes you can get electron movement within a molecule. That's possible, and we'll see examples of that. Or if a sigma bond breaks, then that electron pair goes to an atom. Now, there'll be a more complete list in the videos, in the arrow pushing videos. That's what we're doing here. We're arrow pushing. We're not actually pushing arrows, we're electron pushing. But I'm stuck with the name, so there it is. Okay. You remember the definition of the pH. We'll do some review. pH was developed by a chemist / biologist named Sorensen, and he was sick of scientific notation for very small concentrations of hydrogen and hydroxyl ions. So he invented this mathematical transformation, and he called it pH. Little p, big H. So we know the pH scale is pH 7 is neutral, right? And if we go this way to a more acidic pH, we go down in number, right? We decrease. If we go this direction, right, with a larger number, we go basic. And that can go up to 12 or 14. Let's see, just to balance it, let's go up to maybe 13. So that's what the pH stands for. Well, we also can use, this is just a mathematical expression. So we can also do a log transformation here of the K value for the acid dissociation. If we do negative log of the Ka, we get pKa. And similarly, the smaller the smaller the pKa, the stronger the acid. So very small values for pKa are going to be a strong acid. High values of pKa are going to be weaker acids. And if we take that into consideration and put that in terms of an acid-base reaction, then as the base approaches the acid, if the acid has a very low or small pKa, the reaction is going to be favored toward products. It's going to produce the conjugate acid and the conjugate base with this reaction. Okay. There we go. Let's see. Yeah, and also remember that the P transformation is a logarithmic transformation. So if your pH is 7 compared to 6, what does that mean in terms of the number of hydrogen ions that have been produced? Actually, the hydronium ions, but well, it's a change of 10. Each unit of pH change is a change of 10. If it goes smaller, you're increasing by 10 factor. If it goes bigger, you're decreasing by a 10. And you can think of that also for pKa's, right? The strength of the acid. If a pKa is, say, I don't know, if a pKa is, say, 10 to the minus 6, and you compare that to an acid that's 10 to the minus 7 pKa, this acid is 10 times as strong as that one. So we've got an example here. Trifluoromethane sulfonic acid. Oh, it copped out. They didn't draw us a structure. Okay. Well, compared to ethane, ethane has a pKa of 50. Compare that to the trifluoromethane sulfonic acid minus 13, and you got a 10 to the 63rd times difference in their strength. That's a pretty big difference. So if you have both of them in solution together, which one's going to be the proton donor? The trifluoro is. Yeah. There is a competition. Yeah. We're going to talk about that. Second semester. In fact, that's one of the first things we talk about. Competing reactions. We're going to talk about them as if they're pure right now. And then we'll throw them together in the mix and see how they react with one another. Okay, what should we expect from the outcome of a proton transfer reaction? Well, we've looked at the one already where the strong acid reacts with a strong base. And that actually, you can take the flip side of that coin is a strong base is going to drive the reaction toward products also. So it depends on comparing the pKa of one and the pKb of the other. Remember what the pKb stands for. It's a negative log of the Kb. It's more review. So what would a Kb be? Well, if a Ka does this and yields, well, let's be kosher with this one. It yields this anion plus the hydronium. Well, the B would be some base reacting with water, and it strips a proton off of that water and makes Hb plus OH minus. So if the Kb is very large, we're favoring products as well. Excuse me. Kb is small, right? No, it'd have to be large. The Kb would be large. The pKb would be small. Right? So if you you've got a competition there also. So in the second one, where we have the hydroxyl reacting with ammonia, and the pKa for ammonia is relatively large, so it's a very weak acid. But the strong base equal. Let's see. All right, we're just comparing acids here. I'm sorry. I'm starting to confuse you, aren't you? If I'm confusing myself, I know I'm confusing you. So if we just look at the acids themselves, the pKa for ammonia is 36. The pKa for the conjugate acid of the base is 14. So that means the stronger acid is water. Water is a stronger acid than ammonia, which means the reaction will be driven to the left. Yeah, let's leave it at that. Let's talk about it in terms of acids rather than introducing the concept of bases right now. We could look at it in terms of base strength, but I think if we focus on the acid, we're going to get the same results without so much confusion. So we're comparing the pKa's of reactant versus product acids. And that tells us which side of the reaction we can expect. All right, so predict which side of the reaction is favored. To what extent is the side that is favored? Okay, so let's compare. What's that acid on the left? Recognize that one? That's acetic acid. Okay, sometimes, in fact, a lot of textbooks now in general chemistry will present acetic acid as an acid. Now they have a hydrogen here. That's the acidic hydrogen, C2H3O2. That tells you it's an acid, of course, but that doesn't tell you much about its structure. When I learned it like this: methyl group and then a carboxylic acid group. That was much more useful, and that's what we're seeing here. We didn't show the fact that this oxygen had 2 lone pairs. And when it reacts with methylamine, which is the proton acceptor, it's going to be the base. So how do we move electrons in this case? Well, you don't want to move electrons from the acid to the base. If you're going to form a bond, it's best to move the electrons from the base to the acid. So if we do that, then we end up with the, I'm not sure what we call that. Let me see if they tell us. No, they don't. Well, the base is the methylamine. So the conjugate acid would be the cation. Methylammonium, maybe? No, that's methylamine cation. And then we have the conjugate base for the acetic acid. Well, since we don't have the pK values for those, it's difficult to say which one is which. But if we were given the values, table 6.1, does that give us? Oh, that's in the appendix of the book, table 6.1. So you have to look it up in the book. So if we looked it up in the book and found that the pK for acetic acid is 4.75, and the pK for the methylamine cation is 10, that means that the stronger acid is the acetic acid, and the reaction is going to be favored to the right. Yeah. Okay, so the product side is favored. And what else did they ask us? To what extent? Okay, what they're asking there is, what's the difference? Right, the difference between 10.63 pKa and 4.75, right, is 8, another 8, and then this is 5. So that's the difference in pK values. Well, if we put that back in our formula, right, 5.88 equals negative log of, since we're using a delta here, we're going to put a delta here, delta pK, delta, no, delta H plus, right? Now, delta K. There we go. So you remember how to work those problems? How do you go backwards? You got to move this negative sign over here, and then Ka is equal to the negative power of E. So 5.88, let me change the sign, and then I'll do E to the X. So that's 2.79 times 10 to the minus 3. That's not going where I wanted it to. Oh, I know what I need to do. You probably know, don't you? Isn't this the power of 10? Yeah, that's the power of 10. 10 to the 5.88 equals what? That tells us how many times um, the 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 strength of the two differs by that much. There we go. This is 7.59 times 10 to the 5th. That's how many times stronger the acetic acid is than its competing acid. So this is highly favored to the right. I mean, by what? 5 orders of magnitude, almost 6 orders. I should have looked at the slide. It would have told me what to do. Okay. Oh, we are going to talk about bases, determining base strength. And here again, this is the same thing I told you earlier. The stronger base is the one that has the weaker conjugate acid. So which base is stronger, H minus or HC triple bond C minus? That's the anion from the dissociation of one hydrogen from acetylene. So the conjugate acid of H minus is H2, right? If H minus, so how would it get that minus? It would have to have 2 electrons, right? If we did the formal charge on that one, it would be 1 minus 2 would be minus 1. So that gives us a charge of minus here. That means it will accept a proton. That makes it a base. Okay. How about the other one? It's probably a base also. Right, so this one must have also, let's see, 1, 2, 3, 4, 5. So let's see. It's we do I was going blank. Valence, do valence electrons. So this one has 4 valence electrons, minus 1, 2, 3, 4, 5. That gives us a minus 1. Okay, and this is also a base. We want to see which one's stronger. Okay, which base is stronger? The conjugate acid of H minus is H2, which has a pKa of 35. So the conjugate acid of this one is H2 with a pKa of 35. And the acetylene has a pKa of 25. So this is our acetylene molecule with a pKa of 25. Okay. Before, if we were comparing acids, the stronger one had the smaller value. In this case, this is the stronger acid, so it'll have the weaker base. So in this case, you just compare the numbers. The smaller number gives you the weaker base. If the pKa is less here than it is there, that means this is the stronger base because the conjugate acid is weaker. Okay. Conjugate acid weaker, base stronger. All right. We're getting into a discussion now of what effect the solvent has on a reaction. Remember when in general chemistry, when you're talking about acids and bases, you could not ignore the solvent, right? Because it was usually aqueous. Right? The solvent was there all the time doing its thing. Remember, water, the pKw is 14. Now the pKa might be something else like 4 point, what was it for acetic acid? 5.75? Yeah, 7.5. 7.5. But these are both going on at the same time. There's always the possibility of reacting with a solvent. So suppose you have a reaction going on and you don't want the proton to transfer. The particular reaction you're interested in would be you'd get the wrong product if you allowed proton transfer. Okay, so we pick solvents that are aprotic. Right, they don't have just easily dissociable hydrogens. They might have hydrogens, but they're really tightly bound. Or they don't have hydrogens at all. That's even better. So what that does is it interferes with the desired reaction. In other words, the reactant that you want to react with another reactant is stolen by the proton transfer. And they're calling that the leveling effect. The undesired proton reaction is a result of what's called the leveling effect. Now, the proton reaction isn't the only leveling effect, but that's one major one to consider. If you're, okay, let me just read the statement. The strongest acid that can exist in a solution to any appreciable concentration is the protonated solvent. The strongest base that can exist in the solution is the deprotonated solvent. So if you've got a, the proton transfer reaction can occur as a consequence of a proton donor in your environment or as a proton acceptor. So you want the solvent, if the solvent has protons, you want it to be fully protonated and it doesn't want to give up the protons easily. And if you have a base in your solution, you want one that does not accept protons easily. I hope that makes sense. Probably have to look at examples for it to make sense. So here we have an example with water. No acid stronger than H3O plus and no base stronger than OH minus can exist in any appreciable extent. So in the first case, we favor the formation of the hydronium ion and the chloride ion because we have a strong acid. If the base is stronger than the hydroxyl, in which case we have that anion, the dimethyl nitrogen anion would is a stronger than hydroxyl. So if we have that one and hydroxyl in the same solution, the preferred reaction is the one with the nitrogen. So we compare the strength there. And that favors the production of the dimethylamine. So this gets us to the point of how do you choose the correct solvent for a reaction? What we want in the example that was given, we want the proton transfer. We just want the proton transfer between the species that we choose, not the undesirable transfer. Okay. So if we limit our scope to just proton transfers, then it makes the problem a little easier. If a reactant happens to be a stronger acid than the solvent's conjugate base, then R must have a lower pKa. If R is stronger than the conjugate acid. And that would make R unsuitable. If R is a stronger base than the solvent's conjugate base, then it would also be unsuitable. I need an example. I don't know about you, but I need an example. Say we have this dimethylamine anion is a strong base. All right, we've established that. The diethyl ether is let me move this out of the way so we can see it. Well, I can see it here. You can't see it up there. Is a suitable solvent for this according to the leveling effect. What we're saying is that the diethyl ether is a weaker base than the dimethylamine anion. All right, I got it in. I can't read it now. Okay. So if we look, actually, I think it makes more sense to look at the reaction. If we've got these two species in solution, and we should have a lone pair on that one, shouldn't we? 1, 2, 3, yeah. We should have a lone pair there. And we react that with diethyl ether, or we have diethyl ether in the reaction vessel. Then we have CH3, CH2 with the ether bridge, and then CH2 and CH3. What can we expect there? Well, one possible reaction, it would put CH3 2 in 8. And that would release a hydrogen from this diethyl ether. And what we want to choose is the hydrogen that's the most acidic. Okay. This, you may have, remember when we talked about oxyacids? Well, hopefully. You talked about oxyacids in the acid-base discussion. In general chemistry, the more oxygens you have in the molecule, the stronger the acid, because they have an electron withdrawing effect and they weaken the bond with the hydrogen. So the one that's closest to the oxygen is going to be the proton donor. That means we got this one left behind, and the proton comes from this one, not that one. It could come from this side also. We just arbitrarily picked that one. And that gave us a formal charge here of a -1. Okay, now that we've got that possibility, that reaction established, which is the stronger acid? The stronger acid is this one. This would be, let's see, if this is the stronger base, this is the weak acid. This would be the stronger. This would be a strong acid. This would be a weaker acid. So if we compare these two, wait a minute. Proton donor, here we go. So this would be a stronger base than that one, and this would be a stronger acid than that one. So this being a stronger acid drives the reaction back this way. So this reaction is not favored. Does that make any sense? Yeah. I think that's what he's trying to say here. So what that means is that this reactant would be predominant in this, if this is your solvent, right? If you used diethyl ether as the solvent, then you could put this in that solvent and expect to have this react with something else, because it would not be competing with this one. Okay. I've convinced myself. Did I convince you?
Yeah.
Okay. All right. In probably the second semester general chemistry, you get into the topic of equilibrium. And remember, equilibrium is not static. It looks static from outside. Like there doesn't appear to be any changes in products and reactants. But equilibrium is actually a balance of the forward and the reverse reactions. So if they're occurring at the same rate, you're at equilibrium. Now, both of these, in this example, we've got ethanoic acid is the IUPAC name, but grandfathered in is acetic acid. I guess if you go to Europe, they'll probably call it ethanoic acid. But over here, we still call it acetic acid. So the concentrations of the reactants and products don't change. And we'll see a little bit of acid versus and some of the conjugate base. And the way we quantify that is with the Ka values. Right. Remember ICE tables? Yeah, okay. Calculating the exact position of a reaction after it reaches equilibrium. Yeah. Okay, and we know what Le Chatelier's principle is. I mean, it's a generalized discussion of what happens when you disturb or you stress an equilibrium system, right? The system will respond to minimize that stress. So there are basically three ways you can stress a system. One is you can change the concentration of any of the reactants or products. Once it reaches equilibrium, if you say add a reactant, it's going to shift it to the product side. If you add a product, it's going to shift to the reactant side. If you remove a reactant, it's going to shift to the reactant side. If you remove a product, it's going to shift to the product side. That's concentration effect. Then you have the possibility for, let's see, concentration, temperature. You can change the temperature, which will change the K value. It might change the K value. The only way it changes the K value is if your reaction is endothermic or exothermic. Okay. Which will also shift the reaction. And then pressure. And pressure is only valid as a stressor if there are unequal moles of gas on the product side versus the reactant side. If you have the same number of moles of gas on both sides, then a reduction in volume or an increase in volume, which changes the pressure according to Boyle, will change the equilibrium position. Right? If you pump in an inert gas or you pump in a gas that's not part of the reaction, it won't have any effect on the reaction. Right? So that's Le Chatelier's principle. This is a refresher on what pH is. Right? We already talked about that. Lowering the pH of the solution shifts the equilibrium toward HA. And raising the pH of the solution shifts the equilibrium. So that's a good place to let's say we have this hypothetical molecule. If it's a complex molecule, like a big group out here, and it's got a hydrogen there, then well, we can't put water in there because it may not be water. So let's break the rules again and say we could have this and that. Right? So we would have those two electrons there. Okay. If we wanted a situation, a reaction, which was a protonated compound, right? In order to go in and react, we would have to add protons somehow. Add protons. That would drive the reaction back here. Then we would have most of our reactant in that form. Right? But if we needed the base form, if we needed this form, then we would add maybe hydroxyls, and that would remove that from this side and drive it over to this side. Now our reactant would be the base form. Okay. You see that in pharmaceuticals. How do you get, most pharmaceuticals are insoluble in water, right? They're just huge nonpolar molecules. Well, the only way you can get them to dissolve is to either protonate them or deprotonate them, make them slightly ionic somewhere. So it depends on whether you've got exposed nitrogen groups or not. Usually if you have an exposed nitrogen group, you'll remove a proton. But if you have no nitrogen or no sulfur groups sticking out on the outside of the molecule, then you'll usually add hydrochloric acid. So you see the drug name hydrochloride. That's what they're doing. They're favoring one side or the other. If it's neutral here and you add acid, you're going to make it protonated and charged so that it will dissolve in water. Okay. Acids have different ionization states. Now, what do we mean by that? The dominant ionization state depends on the solution's pH. Oh, this is a continuation of what I was discussing before. Okay. If you change the pH of the solution, if you decrease the pH by adding these protons, then you're going to drive the reactant to this side. It's going to be protonated. If you increase the pH, then you're going to remove protons and you're going to favor this side. It just depends on what form of the reactant do you need to accomplish the reaction. And you can do that by adjusting the ionization state of your molecule using pH. Now, the other thing you have to consider is how do you adjust the pH? I mean, can you use hydrochloric acid? Very often you can. But if chlorine is going to be involved in the reaction, that may or may not be a good idea. You might have to use a different form, say nitric acid, assuming nitrate's not part of the reaction. So there are many factors to consider when you change the pH. You can't just add protons independent. Right? It doesn't happen that way. There has to be a counter anion to go with it. Okay. Remember chemical equilibrium. Right? How do you write the mass action equation? Anybody have trouble with that? Okay. We'll just do a quick example. It may have been a while. So we've got this reaction. This is the one I usually use as an example. Reactants and products. The K for this reaction is the concentration in the numerator, the concentration of C. And if I use square brackets, that is implied molarity. And raise it to the coefficient power, multiplied by the other reactant, raised to its coefficient power. Then in the denominator, we put the reactants. So we'll have A here and B here.
Why do
Why does that one? It's too busy. Yeah, it's way too busy. Simple is better. Yeah. I mean, some reactions are that complicated, but when we're trying to refresh our memory, that's not the way to do it. And remember that K values have these subscripts, and some of them are reserved. Generally speaking, we write KEQ if it's just any reaction here. Ka is going to be acid dissociation constant. Right? Kw is reserved for water. That's water dissociation. Remember solubility products. Okay, KSP or KF. Formation constants for complex ions. Right? Those are examples. But they're all based upon equilibrium. Oh, the other thing, if any of these are L's or S's, liquid, pure liquid or solids, don't put them in the expression because they do not change concentration. The other option you have is if they're all gases, you may want to create this equilibrium expression and call it KP using partial pressures. You can use partial pressures in here if they're all gases. Okay. So what would it look like for an acid-base reaction? If we have an acid, a proton donor on the left, and we have a base reacting with it, and it produces the conjugate base for the acid and the conjugate acid for the base, then we follow the same pattern. Products in the numerator, reactants in the denominator. And this is usually has a single power. It's first power for everything. The reason for that is reactions occur one proton at a time. They don't occur 2 protons, 3 protons at a time. So what would a large KEQ mean for this reaction? Well, it would favor the products. If you have a large K for that expression, since the products are in the numerator, that means the KEQ, if it's large, favors products. And if it's small, it favors reactants. If it's close to 1, now it doesn't have to be exactly 1, but if it's close to 1, it's a reasonably balanced between the two. We might even be able to say, in fact, for this expression, 1 might be the balance point between the two. have exactly the same concentrations on either side. Why? Because they're all first power. Now, in other expressions where you have possibilities for 1, 2, 3, 4, 5, 6 here, and they enter in there, you can't say that. Only if the value is extremely large do we favor the products, extremely small, we favor the reactants for any other reaction. Okay. So if we restrict ourselves to talking about the acid being placed in water, then the acid has the potential to donate a proton to water, produce the hydronium ion and the conjugate base for the acid. And the expression there would be the conjugate base times the hydronium over the undissociated acid. So that's the Ka for that acid. They call it the acidity constant. I think that's okay. But it should be the acid ionization constant. Because you have to ionize an acid. You have to break that bond. As opposed to bases, you just have to dissociate them. Bases are all ionic compounds, like sodium hydroxide, sodium ions and hydroxide ions. You dissociate that one. But for acids, you have to break the covalent bond. Okay, when you compare two acids and their Kas, the value, if the Ka is larger, that's the stronger acid. We've said that earlier. I guess it doesn't. It bears repeating. Are your slides following along okay? Yeah. Oh, we have extra slides here? Okay. 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 Yeah, I need to go in there. In fact, I probably need to do it for both courses. I don't think I've changed them for 211 or 212. So hopefully by the next time. Well, no, I think I taught this last summer. I think we were using the 3rd edition then also, but the students didn't complain. Not that complaining's a bad, complaining can be good. Yeah, I appreciate it. So a larger value of Ka corresponds to a lower value of pKa, simply because of the log transformation. And the reason for that is the Kas are generally something times 10 to the minus power. And that leaves you with a negative log. And Sorensen didn't like negatives either. He didn't like large or small numbers, didn't like negatives, so he just stuck that negative in there. And that made the pKa a positive value every time. Well, actually, if you had, say, a concentration of 2 molar for the acid, the hydrogen ions, then you get a negative value. So we generally don't use pH for very strong acids, or pKa's for very strong acids. They're just, sometimes you'll see them in reference manuals. The strong acid will have a pKa of infinity. Okay. Remember the Henderson-Hasselbalch equation? Remember how to derive it? If I ask you to do that? Okay. So the Henderson-Hasselbalch equation, Henderson came first with his expression. And we start with the reaction. We say the acid dissociates into hydrogen and conjugate base. Now we know that's not right, but for calculation purposes, it works just fine. Okay. Well, Henderson was interested in the concentration of hydrogen ions, because by that time, the scientific community recognized that acidity was a direct result of hydrogen ion concentration. So he just solved the equation for hydrogen ions. Hydrogen ions then would be, let's see. No, write the Ka first. The Ka for this reaction would be H plus times A minus over HA. Okay. And Henderson wanted to focus on the hydrogen ion concentration, so he just solved this equation for hydrogen ions. So he said, I'll put it over here. No, I better put it down here, and then I'll work the rest of it over there. Solving for hydrogen ions. So this requires some algebra. This is the Ka times HA over A minus. Okay. So this was Henderson's contribution. And shortly after Henderson proposed this, Sorensen came out with his P transformation. So Hasselbalch came along and took this part, and he said, all right, I'm going to take this equal to Ka HA over minus, and we're going to take the negative log of that entire equation. So we're going to say negative log, I'm trying to keep them running off my board here, negative log of the entire thing. So what does that give you? Well, the negative log of hydrogen ions is pH, right? And the negative log of Ka is pKa. But what happens when you take the log of X time or A times B? It's the same as the log of A plus the log of B. Right? That's one of the log rules. So that would be pKa for this one. And we're going to leave this one alone. So that's plus here. And then we're going to save this one, say negative log of HA over A minus. Okay? Well, it's too easy to mess up an equation with a negative sign in it. So we get rid of the negative sign. How do you do that? Well, the log of A over B is the same as negative log of B over A. So we just change the sign here and flip these. So this would be plus the log. Now that we change the sign to positive, now we put conjugate base over the undissociated acid. And this is the Henderson-Hasselbalch equation right here. Now, the nice thing about it is it tells us several things. If we're creating a buffer using a weak acid and its conjugate base, what happens if the conjugate base concentration, we choose the buffer, so the conjugate base is equal to the undissociated acid concentration in solution? What happens to this equation? Well, that's this one divided by that one is 1. And what's the log of 1? 0. So that means when these are equal, the pH of that solution is equal to the pKa of the acid. That's what, I don't know if you guys did determine the pKa of, say, acetic acid in class. You titrated it, and for every volume you added, you checked the pH, and then you plotted it, right? So you plot it out like this. Let's see, added base, and then this is the pH, And for acetic acid, it'll do something like this, like that, like that. Well, if you wanted to know what the pKa was, you found out where the equivalence point is, and then you take half of that volume, and there is where you read the pKa right there. Is that enough refresher? That's enough for now, yeah. Okay. All right. So let's make room for the next topic. Well, continuation of this topic. I'm going to leave the Henderson-Hasselbalch here by itself and just erase the rest of it. But we might need that. So for a proton transfer reaction, where you have a proton donor, HA, and the base that's going to receive the proton, the KEQ then is going to be the difference in the pKa's power of 10. That makes it a whole lot easier to deal with. If we want to know what the KEQ is for that reaction, this acid-base reaction, all we need is to get the pKa's of the HA versus the HB. Yeah, and subtract them. Okay, and then make that your power of 10, and that's going to be your KEQ. If HA is stronger acid, is the stronger acid, right? Then we should expect to end up on the product side. And the change in pKa should be positive. We're going to subtract. Remember what we say for delta. Anytime you calculate delta of anything, we say it's final minus initial. You know, that goes for thermochemistry when we had final temperature minus initial temperature. There are other examples, but that's generally what we mean. So when we're saying the change in pKa, we want the final, which is the pKa of the HB, minus the initial pKa of the HA. And then that becomes your power of the 10 for calculating the KEQ. Those are not comfortable chairs, I know. If I could find one, I'd get you a cushy one too. So what we're saying is that if HA is the stronger acid, then pKa is lower. And the pKa for HA then would be subtracted from HB, and we get a positive value for the change in pKa. So what that would give us is 10 to a positive power, right? Very large KEQ. And a large KEQ means the product side is favored. But if HB is a stronger acid than HA, then we get a negative value, and that's 10 to a negative power. And that gives us a value that a KEQ that favors the reactant side. So that's a useful tool to have. Just determine what the now how would you do, say you were given say we've got this reaction B minus, and we're going to transfer and give us an A minus and HB, and this is probably given to us Ka or pKa, and we can calculate the Ka. That's not a problem. But we want to know what this value is. But we're not given, we're given the KB for this one. How would we calculate the Ka for that one? Remember that formula? KB equals 10 to the 14th divided by Ka. Or you could put Ka on this side. It worked just well. In fact, since we're looking for Ka, we should do it this way. 10 to the 14th divided by Kb. So you would divide Kb into 10 to the 14th, and that would give you the Ka for this value. Then you could compare them. Just in case you get a sneaky question like that pop up on a test. I don't know. I probably ought to look at the exam because I haven't looked at it since last summer and just see, because this last one, didn't I find the error in the exam? Yeah, there could be another error in there. Oh, it should have been nonpolar and the word polar. Yeah. Tetrahedral. Yeah, that was okay. But it was carbon tetrachloride. Should have been nonpolar and tetrahedral. And it said polar and tetrahedral. And 3 of you guessed right. But I gave everybody credit anyway. Okay. Remember, excuse me. Remember the discussion in general chemistry of entropy and Gibbs free energies. Josiah Gibbs was interested in working with thermodynamics, as many people were at that time. And he came up with this expression. Well, actually, that's not the expression he came up with, but it works for determining the Gibbs free energy for any reaction. And let's see if I can remember it. Delta G equals delta H minus T delta S. So this is entropy, this is enthalpy, this is the temperature at which the reaction occurs, and this is your Gibbs free energy. So what do we know about the sign of that Gibbs free energy? If we calculate this and we come up with a negative here, that means the reaction is spontaneous. A negative delta G means spontaneous. Now, if we calculate the delta G for a reaction, then all we need is the Gibbs free energies for the products, add them all up, and don't forget to multiply by the coefficients, because the Gibbs free energies in any table are for 1 mole of reactant or product. So if they have a coefficient, you have to multiply that times, and you add up all the product free energies and subtract the reactant free energies and gives you a value. If the value happens to be less than 0, then it's exergonic, let's say. Kind of like exothermic. It gives up energy. It releases free energy. If it's the other way, if it's positive, then it's endergonic, and you got to put energy in. It absorbs free energy. And this is what the free energy diagram would look like. And we're going back to our acid-base reaction where we have HCl plus hydroxyls. And there's an energy of activation that produces the transition state. Remember when I drew that example where we had the dotted bonds? That's going to be at that point. So we had Cl, H here, then over here, that. Partial plus, actually, not a full. Anyway, this would be a transition state. And that transition state takes a certain amount of energy. And that's usually dependent upon temperature. Not always, but usually. And once you get to that transition state, then you can go over the hill and you go down to the free energies of the products. And the difference there means that the reaction on the left, as it proceeds, is exergonic. The one on the right is the reverse reaction. So you could either draw that one on the right, or you could just focus your eyes on the products and call them reactants. Then you would have to go backwards. In that case, it takes a lot more energy to get to the transition state than the forward reaction. Okay. So if we have the, and we went into a lot of detail, I think in my textbook that I'm using, it's in chapter 16, we get into entropy and free energy calculations. And this particular delta G for a reaction, if you know the KEQ for a reaction, you can calculate, and the temperature at which you're measuring it, you can calculate the delta G for that reaction. Or if you determine the delta G for a reaction, whether you do the reaction or you calculate it from a proposed overall reaction, then you can calculate the expected KEQ. There it is. There's Gibbs equation right there on the bottom. But this is the relationship between the Gibbs free energy and the equilibrium constant. So if the equilibrium constant is very large, that's going to give us a negative value of delta G. That's why we put that negative there. Very large KEQ means it favors products because it's a negative delta G. If this is a very small number that gives us a negative log, then we're going to get a positive delta G, and that's not spontaneous in the forward direction. Okay. So enthalpy again, enthalpy is, think of it as a potential, because enthalpies don't depend on the path. It's a state function. In other words, you only need to know the beginning and the end. What happens in between is irrelevant for delta H. Now, path functions are like Q's. Actual heat transfer does depend on path, but the enthalpy, the potential for that reaction, only depends on the beginning and the ending states. So if the change in enthalpy for the reaction happens to be greater than 0, then we know that we've got an endothermic process. And if it's less than 0, we have an exothermic process. Breaking bonds always require energy, so they're endothermic. Forming bonds releases energy, they're exothermic. And the balance in the outcome of the reaction, the delta H for the reaction, depends on the balance between how much energy did you have to put in to break the bonds, how much energy do you get back when the new bonds form. That's what makes the overall either endothermic or exothermic. And all these values that we're seeing here are standard values. That's why they have that little 0 up there in the upper right for every symbol. Those are standard conditions. So what would be standard conditions for chemical reactions? STP, standard temperature and pressure. Standard temperature is 25 degrees C. Standard pressure is 1 atmosphere. And then standard concentration would be 1 molar, if that happens to be an issue. Okay. Now, that's for all chemical reactions, except when you're talking about the gas laws. When standard temperature and pressure for gas laws is induced, then the standard temperature is 0 degrees. Okay. Just a reminder. Okay, so what do we mean by entropy? Well, when entropy is first introduced to you in general chemistry, we talk about the degree of disorder. Right? That's not exactly right, but it's a good place to start. So the degree of disorder says if you break a bond, then you're increasing the entropy. Okay, because now instead of one entity, you have two, and that's more disorder. You remember a discussion of microstates? That's the more proper approach to entropy. The number of possible microstates increases, that's an increase in entropy. Okay. But for our purposes, I think the disorder will work just fine. Okay. So now we're going to look at, let's see, how much, you probably can't tell me because your slide set doesn't match mine. Let me see. I think I had a total of 70 something slides. 73. Yeah. And oh, these slides are not numbered, so let me see. 6. Okay, I'm about halfway. And I've used up an hour and a half. Functional groups and acidity. Okay. So each of the functional groups has and essentially has a range of acidity values, of pKa values. So if you find a carboxylic acid group attached to some other group, like for acetic acid, it's attached to a methyl group. For benzoic acid, it's attached to a benzene ring. They're going to be in the neighborhood of 4.5 to 5, in between there. There's an influence on the acidity of that group, that side group, depending on what it's attached to. Now, the top examples there where you have hydroxyl attached to an ethane group or to an isopropyl group, propane 2 group, there's not a significant impact on the acidity. The ethanol is slightly more acidic than the propanol, and that's probably due to resonance. But when you get to the bottom example, where you've got a phenyl group attached to the carboxylic acid, the impact is much greater. There's a withdrawing effect of the phenyl group that weakens the bond between oxygen and the hydrogen. That's why the statement, they tend to be similar, but they're more like a range than they are exact value. Estimate the pKa values for the indicated CH2 protons. All right. Well, we'd have to look it up in table 6.1 using the Ka. We can say one thing. The carbon that's closest to the oxygen is going to have the strongest, is going to be the strongest acidic hydrogen. One of those hydrogens on that CH2 will be a stronger acid than the one for the B because of its proximity to the oxygen. Now, the exact values, we'd have to look them up. All right. Oh, I see what they're getting at also. We're looking at acetone hydrogens. Ketones tend to be in the neighborhood of 20. Acetone is 20. They're in the neighborhood of 20. And then the B one is more like methyl, right? It's significantly far away from the oxygen, so it's going to be like a methyl hydrogen versus a ketone hydrogen. The A is like a ketone, the B is like a methyl hydrogen. So the difference there is between 20 for acetone would be 20, and for methane or ethane would be in the neighborhood of 50. So there's quite a difference there, a huge difference. Okay, what does the charge, what is a charge effect on the acidity of any species? The pKa of H3O plus, that's the hydronium ion, is 0. Whereas the pH of water is 14. The pKa of water is 14. So the H3O plus is much, much stronger acid than H2O. And that makes sense. All right. We know the pK for water is 14. It's very large, which makes it a very weak. Let's see. If it's going to accept a proton, that makes it a weak base. So it's going to produce a strong acid. Whereas the ammonium ion is 9.4, whereas the ammonia molecule is 36. So these charged species tend to be stronger acids. And that's a general trend. If you have the potential for a proton transfer from a charged species, it's going to be more likely to release that hydrogen. It's more acidic than the uncharged species. It's easier to get that proton away from NH4. If we drew the ammonium, right, it's going to have a positive charge. It's going to be easier to remove that hydrogen and produce ammonia, which makes it uncharged. Uncharged tends to be more stable anyway. So the more stable species is favored here. Getting rid of that hydrogen is exactly what it wants to do. So why should the presence of a charge have this effect? They're not going to give us an answer. I think I gave you one possible answer here. All right, we know about the autoionization of water. Right, pure water is going to produce some hydronium and some hydroxyl ions. Very few, actually. There's a very, very large energy barrier to producing the H3O plus ion and the OH minus anion. A huge energy barrier. So what do they mean by keeping track of new charges? All right. Okay, if you have a situation where you count the number of charges, I think that's the point of this slide. The top example where ammonia accepts, it donates a proton to water, produces the hydronium. So ammonia in this case would be the acid, water would be the base. You're producing two charges, which adds to instability. But in the bottom one, where you have the ammonium ion transferring a proton to water, and notice the use of the curved arrows there. We're taking a lone pair from water, and it's attacking the hydrogen, and the broken bond donates the pair of electrons from the bond to the nitrogen and neutralizes that positive charge. So now we have neutral ammonia, and we still only have one charge. So it's two charges versus one charge. The pKa for ammonium, is much higher than it is for ammonia because of the outcome of the ammonia transfer gives you two charges, whereas the transfer from ammonium only gives you one, the same number of charges as before. So and the pKa's bear that out. This is just a trend that you should be looking for, keeping track of new charges. If you create a new charge, then you're likely to be less probable. And this is the energy barrier diagram. So for the one that's with the very high pKa is in the red, the one with the lower pKa is in the blue. Right? It's still endothermic, right? Or endergonic, but it's more probable and has a lower energy barrier for the maintenance of one charge rather than the creation of two charges. Okay. Let's see. What's that word? Oh, with like charges. Relative acidities of protons on atoms with like charges. What we're claiming here, the author is claiming, is that a greater acidity is for positively charged species relative to their uncharged molecules. And ammonium is a good example. So how do we explain the relative acidity of species that have the same charge? Right? All of these factors below contribute to that. What's the identity of the atom that the hydrogen is attached to? Right? The more electronegative it is, the weaker the bond is going to be. Right? It produces a polar bond. And the higher the polarity of the bond, the stronger the acid. Well, I can think of one example where it's not true. Did y'all get this one in general chemistry? Were you looking at the halogens? We have iodine here, and then bromine, chlorine, and fluorine. If you make an acid out of each one of these, how does the strength vary? Okay. The strength varies with the electronegativity. So the stronger acid would be as we go from HI, HBr, Cl. Because the electronegativity is increasing, and the charge density is increasing also, because iodine is a huge atom, bromine's a little smaller, chlorine's a little smaller. So we would expect HF to be a very, very strong acid, but it's not. It's a weak acid. The strongest in this sequence is HCl. So in general, the more electronegative atom produces the more acidic hydrogen. But HF is unique because even though fluorine has the highest electronegativity in the periodic table, it's still, the hydrogen gets even closer to the fluorine because it's smaller. And that strengthens the bond. The closer you can get to the other atom, the stronger the bond. And that negates the effect of electronegativity. Okay, hybridization of the atom has an effect, and we're going to talk about each one of these, I think. So what do we mean hybridization is sp versus sp2 versus sp3. I guess we could keep going on up, but for organic chemistry, we stop at sp3. If there are any nearby pi bonds, they will have an influence on the acidity of the hydrogens attached. And not only the atom that the hydrogen is attached to, but what are its nearby neighbors? We saw that effect with that that last molecule with the carbonyl group on. Right, the hydrogen that was closest to the carbonyl group was a stronger acidic hydrogen. Okay, so protons that are on different atoms in the same row of the periodic table. So we're talking about periodic trends now. As we move to the right, we find that, say we're in the second period and we're going from carbon to nitrogen to oxygen to fluorine. Right? We're getting more electronegative as we go to the right, and we find that the pKa's are dropping. And they drop precipitously from water to HF. So HF is a weak acid, for sure, but it's a stronger acid than water or ammonia or methane. And this is another thing, this is another technique that helps understand whether a particular transition is going to be favored or not. Look at the outcome. So what would the outcome of a transfer of a proton from methane be? Well, it would produce CH3 minus. Okay. Transfer from this species would be an NH2 minus. Okay. And for water, could be fairly, would be OH minus. Go. And then HF would produce F minus. Let's see. Here. Let's see, is that right? 7 minus 8. Yeah, that's right. No. And this is here, here, here. Okay. So what the outcome is based upon, well, the decrease in pKa from left to right can be justified by the electronegativity of the atom that's left over after you remove a proton. So the higher electronegativity stabilizes what's left over. So HF, this is more electronegative than oxygen, which is more electronegative than nitrogen, is more electronegative than carbon. Let's see, carbon should be, let's see, 1, 2, 3, 5. All right, so the stability of the product is something to watch out for when you're looking at whether a reaction is favorable or not. Is the product stable? If the product is stable, it's more likely to occur. And that's the whole, that's what I'm getting at here, even though the slide itself is talking about the increased stability based on electronegativity. There are other factors to consider when you look at the outcome in terms of stability, right? And we'll see that at various times for the rest of this semester and next. Okay. So here's another energy diagram. We're just saying that when we put these species in solution, the transfer of a proton to water gives us these charged species, and the more stable is the one with the highest electronegativity. And we can see that in the energy diagram as well. These are not just drawn theoretically. Well, actually, they're drawn by an artist, but there's data to back them up. Let's put it that way. Okay. So these are atoms in the same row. and we have increasing stability. An anion becomes more stable as the electronegativity of the atom bearing the negative charge increases. Okay, so we're beating that horse to death. Which means with a lower pK, we have a stronger acid. That means that water is a stronger acid than ammonia. They might end up in the same place or similar place, right, as seen from the diagram, but the energy barrier is different. There's a larger energy barrier for the, well, actually, this one is transferring a proton back to water. Yeah, transferring a proton back to water. So that makes the ammonium ion a weaker acid than the hydronium. Okay, we're still in the same row. Now what happens when we try to add a proton to these species, right? Yeah. Increasing electronegativity of the atom bearing the positive charge. The stability of the cation is just the opposite. Yeah. So if we were to go the other direction, why don't we do that? We removed a proton to go that direction. If we add a proton to this side, then we have a CH5. Oh, it doesn't exist. Never mind. We leave carbon out because a CH5 plus doesn't exist. But an NH4 plus does exist. So we could do NH4 plus here, a plus charge. That means we've lost that pair of electrons there. And this one would be add a proton would be our hydronium. Let's see, like that. And we add one to this one, H2F, and that would only have 2 lone pairs now. But these would all be positively charged. The stability increases in this direction. It's just the opposite from the anion. The cation stability is more stable with the lesser electronegative central atom. Now, is there a logical explanation for that? I think so. Because the less electronegative the central atom, the more stabilizing the positive charge is around the entire molecule. Because it's not trying to draw more electrons from its neighbors. It's allowing those electrons to go out and partially neutralize that positive, if that makes any sense. So you have an opposite trend when you go for the cation versus the anion. Okay, what if we have protons on different atoms in the same column of the periodic table? Here's a good example. If you look at HF versus HCl, right? HCl has a pKa of a -7. It's so strong that I don't even know how they get -7 out of that, because hydrogen chloride in water essentially completely dissociates. So the farther down a column an atom appears in the periodic table, the more acidic the protons that are attached to it. All right, now the negative charge is less densely distributed over the larger atoms, which are found as you go down the column. So what that's doing is it's taking the negative charge that is generated by the dissociation of one hydrogen from that molecule, and it's allowing that single charge to be distributed more evenly over the entire molecule. So it increases the stability. Now that seems to run counter to my original idea where hydrochloric acid was the strongest acid. Let's see, are they gonna, no, they're not gonna go any further. Okay. So I don't know if that's going to work with halogens. It might work with some of the other groups. Simply because the larger atom distributes that negative charge over more volume, and that stabilizes the charge. So there you have where you remove a hydrogen. If you can spread that charge over a larger volume, then that tends to stabilize the anion that results from the dissociation. Okay. What effect does hybridization of an atom have? So here we have a comparison of sp versus sp2 versus sp3. And the one on the left is sp hybridized carbon for acetylene, sp2 hybridized for ethene in the center, and sp3 hybridized for ethane on the right. The higher electronegative, effective electronegativity. Okay. Effective electronegativity. We talked about that before, didn't we? Or did I just dream it? Yeah, electronegativity. The effective electronegativity is directly related to the number of pi bonds. So the effective electronegativity increases with the number of pi bonds. So if you only have a sigma, that's going to be the lowest effective electronegativity. A 1 pi bond will increase it, 2 pi bonds will increase it further. What that tends to do is stabilize the negative charge. So the acetylene, I would expect the acetylene to have a smaller pK than either ethene or ethane. No, it didn't say. Well, that's cheap. Did it say in the first edition slides, or does it just skip over that? We're just okay. The author is just giving you a trend for hybridization of atoms. So the sp hybridized is more stable to negative ions than the sp2 or the sp3. Now we haven't talked about positive ions yet. If you could make positive ions out of those, then my guess is it would be the opposite trend. How about adjacent double and triple bonds? Okay, in this case, we're not talking about just effective electronegativity. We're talking about resonance effects. So if you have an adjacent double bond, right, it's one carbon removed, it's one atom removed from the hydrogen. The hydrogen's attached to the oxygen, and what's attached to the next atom? In this case, there's a double bond. This offers us the possibility of resonating with the oxygen. And I'm not sure if it's going to show that. Let me see. Look ahead. Yes, it does. Okay, so on the next slide, we're going to show the resonance. Whereas ethanol cannot resonate. So it's not as the loss of a hydrogen from acetic acid gives rise to a more stable anion because that extra charge on the oxygen that's left behind can resonate with the carbonyl group that's next door. Okay, that in one statement, that's what we're getting at. So it looks like this. If we lose a hydrogen, transfer it anywhere you want. then what do you end up with? You end up with a negative charge. You end up with 3 lone pairs on the negative charged oxygen, and that can resonate with negative charge being switched to the other oxygen. So this would be a good time to use curved arrows inside a molecule. So let's say we end up with this species, and this one, there, they're negative charge, right? Okay. What happens then is, excuse me, at concerted, we move 2 pair here, right there, and these 2, because look what happens. If we use a curved arrow and move these 2 here, what does that do? That creates another bond here. 1, 2, 3, 4, 5. You can't have 5 bonds on a carbon. So this bond has to break. And where we originally had 2 lone pairs there, now that one produces 3 lone pairs. This one forms a double bond here with 2 lone pairs. It's not charged anymore, right? Because oxygen would be 6. Yeah, 6 minus 1, 2, 3, 4, 5, 6 would be 0. So 0 charge here. And this oxygen now has that. And this is 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is minus 1. So it resonates back and forth between these 2. Now, they don't use curved arrows there, but I thought this was a good opportunity. As opposed to the bottom one, where the ethoxide anion is formed by the loss of a hydrogen, the negative charge is stuck on that oxygen. It can't resonate with anything, which means it's less stable. It's localized to the oxygen atom. Whereas if you can resonate, then you add stability to the species. Now, later on, we're going to see possibilities where you get resonance structures, and the resonance allows you think you have this one to begin with, and then it resonates to this one. That's the reactive species. So resonance can produce reactive species, not just stabilize a charge. Okay. And if we look at the charge density diagram here, we see that the ethoxide ion has all that negative charge concentrated on one oxygen there, whereas that charge is spread over the 2 oxygens because of resonance. So when we draw these resonance structures, we're not saying that it's either this one or it's that one. We're saying it's both. And that produces a stronger acid. Acetic acid is much stronger than ethane. Here's another possibility for stability. The acetic acid, the acetate ion, is more stable than ethanol, but the sulfuric acid is can resonate among 3 oxygens, which further stabilizes it. If you can delocalize over 3 oxygens versus 2, that makes sulfuric acid a much, much stronger acid than acetic acid. Okay, so resonance plays a huge part there. Now, when we're looking at the acidity of compounds that have neighboring electronegative atoms. Oxygen's included there. The halogens are included. To a lesser extent, nitrogen, sometimes sulfur. They have an electron withdrawing effect. So when we say F oxide, right, which would be the anion from ethanol versus 2-chloro-F oxide. So what we've done is just replaced one of the hydrogens on the second carbon with chlorine. And chlorine is more electronegative than hydrogen. It's going to have a withdrawing effect. It's most pronounced if it's only one carbon away. Right, so that chlorine is attached to carbon 2. If this were a propanol and we put a chlorine on the third carbon, the effect would be very, very much reduced. But this is called the inductive effect. Okay. That's just an illustration of what's happening. The anion, as a matter of fact, what's happening is you're withdrawing some of that charge away from the oxygen, which stabilizes the negative charge. It's spreading the charge toward the chlorine, which stabilizes the anion. And the more stable the anion, the more acidic the acid. Now, just the opposite effect occurs if you protonate that hydroxyl group. If you protonate the hydroxyl group and you try to remove more electron density from it, then that destabilizes it. Right, so the inductive effect on anions is to stabilize, and on cations is to destabilize. Okay. I think this was the last one, the electron donating groups. Most electron donating groups are alkyl groups. So when you compare the electronegativities, the dipoles of the bonds between carbon and hydrogen, you find that it's slightly toward the carbon. Carbon is a little bit more electronegative than hydrogen. And that allows the electron donation through the carbon to whatever else it's attached to. So that's a discussion of certain electron donating groups. The alkyl groups happen to be part of that. In this case, we're talking about the methyl group, but the ethyl groups, the propyl groups, they can have a similar effect. Not exactly, but close. And then, let's see, I went the wrong direction. Here we go. Depending on whether your formal charge is on the atom they're attached to is negative or positive, is it an anion or cation? If you attach donating groups to that anion, that amide anion, then you destabilize it. Okay, because it's trying to donate electrons to that nitrogen, and the nitrogen doesn't need any more. It adds more negative formal charge to that nitrogen, and it destabilizes that one. So you don't want, if you're trying to stabilize the anion, you don't want methyl groups attached to it. You want to stick with the hydrogens. Or an electron withdrawing group or atom, like chlorine. If you attach chlorine to that, then it would stabilize the anion. Okay. That was for anions, and I mentioned cations already. So if you have, if you replace the hydrogen in this ammonium with a methyl group, then you stabilize the cation because it's trying to donate electrons to that cation and stabilizes it. So methyl ammonium would be more stable than pure ammonia. Maybe that's why quaternary ammonium compounds are used. Right? You know that ammonia, if you open a bottle of ammonia, you're going to smell it. If you open a bottle of quaternary ammonium cleaning compound, you may get a slight whiff, but it's not going to be debilitating. A friend of mine's wife decided she was going to create a super cleaning compound. She took a bottle of ammonia and a bottle of bleach and put them together. And she cleaned the bathroom in the enclosed room like that. She went to the hospital. Yeah. Okay. Oh, yeah, the bathroom was spotless. Okay. Summarizing the inductive effects. The magnitude of an inductive effect caused by an uncharged atom depends on the atom's electronegativity. We know that. Any charged substituents have more pronounced inductive effect than uncharged substituents. So if you attach not a neutral substituent like methane, say you attach, I don't know, a hydroxyl, or you make the molecule charged with the addition, then the inductive effect is going to be more pronounced, either donating or withdrawing, one or the other. And if you have multiple in inductive pathways in a molecule, they are additive. The total effect is additive. That's why your that trend in oxyacids, the more oxygens you have, the greater the acidity. So if I have H2SO4, it's more acidic than H2SO3. Right? Sulfuric acid is more acidic than sulfurous acid because it has one more oxygen. So there's the inductive effects are additive. And I mentioned this one before, those effects fall off very quickly with distance. So if they're within, if they're attached, the inductive effect is attached to the second carbon away from the target or the nitrogen, whatever the atom happens to be, then it's going to be a pronounced effect. But if it's three or more away, it's virtually insignificant. Okay. Now we've got a, I don't know, call this a mnemonic device, the Cardinal rule, ranking acid and base strengths by using the Cardinal rule. All right, what's the most, which one of these effects has the greatest effect on the charge stability? Well, okay. Do the species have different charges? All right, if you're looking at comparing two or more species, do they have different charges? A charged species is usually more reactive than one that bears no formal charge. Now, when they say charged species, it could be a bona fide ion, or it could be a calculated formal charge. Either one is valid for this Cardinal rule. Look at the charge first. Then look where the charges occur. Do they appear on different atoms? And then look at the size of the atom, the electronegativities, the hybridizations, and what effect do they have on stability? Then resonance delocalization. Resonance would be the third effect. Oops, excuse me. The third effect. Are the charges delocalized differently through resonance. If the resonance is available, then you can determine whether one species is more stable than the other. And then the least effective is the inductive effect. Look for electron withdrawing groups or electron donating groups. Okay. So if we apply the Cardinal rule to this chart, and I'm not sure if it looks that way in your printed version, but we're close to the end. We're getting close. We'll have time for a lab, hopefully. Oh, no, oh, that's next week. Yeah. Yes, arrow pushing. Yeah. That's why I want you to look at those videos. Okay, so if we follow the relative order of importance and we go from top to bottom, top is more important in this table. We see the charge of the atom changes the acidity of the species. So the ammonium is more acidic than the ammonia. The atom type, if we compare nitrogen versus oxygen, we find that the oxygen produces a more acidic compound. And the atom type also refers to hybridization. So the acetylene is a stronger acid than ethane because of the effective electronegativity of pi bonds. And then the third least important, or third most important, is resonance delocalization. If you can resonate upon loss of a hydrogen, if you can resonate that ion, then it's more stable and it's more likely to accept the loss of that hydrogen. And then there are inductive effects. If you have that last one where you have 3 chlorines on the trichloroethanoic acid or trichloroacetic acid produces a stronger acid by induction than the acetic acid. Okay, the Cardinal rule: charge, atom type, resonance, inductive effect. I'm not sure what the AL is on there for. Did it say on the previous slide? Cardinal. It's probably just stuck on there so that you can remember it. Nobody's going to remember Cardin. A Cardinal might be more recognizable. Okay. Can we apply the Cardinal rule to ranking strength of these 4 acids? All right. So which one would be the strongest acid? If we go for charge first, then I would say C would be the strongest acid. Then charge atom. All right. Which they all have oxygen for the hydrogens attached to them. So that, and there, do we have any, I don't see any difference in hybridization. So we skip over that one. So charge, atom, resonance. Do we have any resonance? Yeah, D could resonate. So it would be the next strongest, perhaps. And then inductive effect. And the inductive effect, where the fluorine in B is closer to the hydroxide than the fluorine in A. So it looks like CDBA would be the order. Let me see if I got it right. Okay, we look at the products. Okay. Okay, it hasn't ordered them yet, I don't think. CDBA. Okay. They're doing it from least to greatest. So I was going from right to left, CDBA. Did I say that right? Let me go back. CDB. Yeah. Okay. Yeah. So using the cardinal rule, we were able to answer the question. Okay. If you know the order of acid strengths, then you can determine the order of base strengths because it's going to be exactly opposite. So instead of CDBA, it's ABDC would be the order of base strength because they're always opposite. The conjugate base of the acid is going to be opposite of the acid strength. Okay. So we're getting into amino acids. What do we hope to gain from that? Conjugate base strength. Structure of amino acids in solution as a function of pH. Oh, okay. Amino acids are a special case. They've got two potential acid or base constituents on the molecule. They've got a carboxylic acid group and they've got an amine group. Right. The carboxylic acid is the acidic group, of course, and the amine group is the basic group. So amino acids, well, I should say the amino group. The amino acids have those two possibilities. Now, at what point will you have neutral amino group and the carboxylic acid group? That's why they're called amino acids. And these are called alpha amino acids. Why? Because there's a central carbon here, right? And on that carbon is that carboxylic acid group, and off of that one is a hydrogen and the amine group. And down here is variable. Okay, so you always have the hydrogen, the carboxylic acid, the amine group, and then this varies with amino acids. You probably remember that from having to memorize all of them. So, if we start, actually in this diagram, if we start at the right, no, wait a minute. Okay. We draw this, but that's not actually what happens. Let's go back to modifying the ion by changing the pH of the solution. So if the acid end of the group is about pKa 2, right, and the amine group is about, and this will vary, pKa 9, thereabouts, 9 to 10. What that means is if the pH is much less than 2, then there's going to be a lot of hydrogen ions in solution, right? And they're going to keep this group right here protonated. But they're also going to protonate this one. So here's what happens. That's going to be neutral. And this is going to have an extra proton, which will add to its charge. Okay. Let's see. That's not going to have any lone pairs on it now. So this is at pH less than 2. So if the pH is between 2 and 9, we're allowing this proton to escape, and now we have a what's called a Zwitter ion. A Zwitter ion is German for both. You got both ions on the same molecule. It's a cation on this end, anion over here. But the net charge is 0. Then if we increase the pH even further, what does that do? Well, increase the pH will give you lots of base in solution, right? Let's see, like that. And what that will do is it will keep this one from being protonated, and it will take that proton off of there. So now we have a negative ion. So the amino acid is a negative ion in high pH solutions. Middle of the road is a Zwitter ion, and pH is less than 2 would protonate both the hydroxyl and the amine group. Let's see, this is aspartic acid. Okay, aspartic acid. Okay, so now we're introducing an acidic group on the R. So this one is going to be like that and like that. Okay. So with the pKa here of a about 2, what's the pKa on that side group? The side group is a little less. Why? Because it's once removed. This is more electronegative than carbon, and this has a tendency to withdraw. No, that's not right. Why is that pKa 3.86? 3.86, where this one is about 2. Oh, I got it. What is this one attached to? Well, this one has an inductive effect from the. They should both have inductive effects from nitrogen. Nah, never mind. That doesn't work. What we're saying is we can have the Zwitter ion if the pH is less than 3.86 because the side group is also acidic. But if we increase the pH above 3.86, now we're going to remove a hydrogen from the side group as well. Right. So instead of just having 3 possibilities, well, 3 possibilities with an R group. So it depends on the R. So once you have the R group, now you have 4 possible structures, depending on the pH and the pKa of each of the groups. So you need to know what the pKa's are. Generally speaking, around between 9 and 10 for the amine and 2 for the alpha carboxylic. And then any side group, you have to look at what's the pKa for those side groups. Here's another one. This one is for lysine. Right. Everybody remember Jurassic Park? Right. They were supposed to have control of the reproductive ability of the dinosaurs by introducing a defect in their genes where they could not metabolize lysine. So they just, if you wanted to kill them all, just remove lysine from their diet. Well, nature found a way. They found lysine somewhere. Okay, so what's the pKa of that the ammonia on the end of that aliphatic group. It's about 8.95. So it's a lot higher pKa versus the 3.86 on the acid group. So we're seeing it's consistent, right? The ammonia group on the alpha carbon is about 9, between 9 and 10. But if we add another ammonia on that other end, what happens to the pKa on that other ammonia? It drops below 9. Now they're calling the Zwitter ion only when you have a neutral charge. If the pH is between 2 and 9, you're going to get 2 positives and 1 negative. So this molecule is a net positive charge at that pH. But if you're between 8.95 and 10.53, you're going to get only 1 positive and 1 negative. Now, what's the advantage of a Zwitter ion? Well, if overall neutral, then it's actually it has an effect on its analytical behavior. So we won't go into that.